All right, welcome back, Precalcsters. This in green on top is what we left off with last week. If you give me any triangle, and you don't need to draw it again, but any triangle, and I'm just going to draw it in quadrant 1 because it's convenient, and you say, hey, here's a theta. I know that thanks to SOHCAHTOA and a lot of stuff that you guys have already seen, we have some distance up here that's a y, and some distance over that's an x, which means this ordered pair can be x and y. And using what we know about SOHCAHTOA without ever mentioning it, we have opposite over hypotenuse, which we just call the radius in this situation, is y over r is sine. And we have these nice definitions. Trig functions are just ratios. They're fractions. And I don't want to confuse you. The trig function sine plugs in a function and it spits out a ratio of the opposite side and the hypotenuse. That's all that it does. Okay, now with that in mind, we're going to use these definitions real quick and just make a little sense out of this. Then we'll do a 10-minute unit circle quiz. Cool. All right, so looking at this, pi thirds, first off, we're just going to make sure we can hit this. Rafa, how much is a half circle in radians? Pi radians is a half circle. So 1/3 of the way through should put you in quadrant 1. 1/3 of a half. So that's weird, but it's a sixth. But 1/3 of half a circle. Now, when I sketch these, and it's entirely up to you if you want to, I'm going to try to sketch them as best I can in the correct quadrant. So this one's nice. Here it is. Pi thirds. Now, if you have to think about this connection with degrees, and it's natural that you guys will want to use degrees still, 1/3 of a half a circle would be how many degrees? 60. So I know I'm about 60 degrees. Now, without anything else, this is where my head goes, and it's my hope that's where your head will go. You don't need to sketch this. 60 degrees is like up here. Is that more up or more right? So if I'm trying to decide, is it root 1 over 2 in the y direction, or is it root 3 over 2? Which one's bigger? Root 3 or root 1? Root 3. So I'm higher up. It better be here. The second I get that 1 point, everything else is free. I know there's my values. Okay. Now, more specifically, if I just draw the triangle, I'm obviously not going to draw it all like this. What's this height? Based on this pi thirds that I drew on the circle. So careful, you're giving me the radius. The height would be this distance on my triangle. Root 3 over 2? I don't know why I gave myself such a small scratch box here. This would be what? The horizontal? 1/2. And then this would be my 1, right? Cool. As we're looking at this, there's some places where I would say maybe you would benefit from showing a little bit of work in the problem, and we're going to see that, I imagine, immediately. If I ask for the sine of this angle T, can you tell me the y value of this triangle? Root 3 over 2. Anybody object? Okay. Root 3 over 2. Now, check it out. We know that, and maybe we don't have it locked in completely, but if I have sine as y over r, to get the cosecant, I just take the reciprocal, right? So instead of root 3 over 2, and this part's kind of annoying, but what would we call this? To get cosecant. And there's only one thing about this that I hate. What's not allowed? I can't have that square root downstairs. Good news is that there's a bunch of choices of 1, and one in particular that's really convenient. JV, if you don't want this to be a square root of 3, what could you multiply the denominator by? Good. And I have to do it to both of them, right? And check it out. Here it is. What is the cosecant of pi thirds, apparently? And that's an everybody question. 2 root 3 over 3. Cool. Doable, or am I going faster than I should? We'll find out momentarily. Because talking with your neighbors or partners, Sean, you can move, and Riley, you can move if you guys don't want to be on islands. Rafa, same is true, but you're usually on an island back there. I want you guys to answer the cosine and tangent, and then in turn, also get the secant and cotangent. I'll give you a moment. All right. So if you are not finished with the original or the second, just hold off because we're going to do our quiz here in just a second. But let's talk about this first one. I just want to see what shakes out, and maybe this is a good thing for people to work on after the quiz if you finish quickly. Okay, for the cosine of angle T, we defined cosine as x over r. The radius in this is 1. What's the x value? And am I losing people with this question? We'll be more specific. JV, from this angle, pi thirds that we just formed, how far in the x direction must you go? Okay, and I'm going to write this and immediately erase it, I think. But that's the x, right? 1/2. And then I'm going to write one more thing, but I'm going to erase it. It's over the radius, right? What's the radius? Do I really want to write 1/2 over 1? Not particularly. Would I count it wrong if you did? No, but I guarantee I would write a comment on your page. Cool. All right. If we got the cosine, the secant's easy. 2. We literally just flipped it. No rationalizing needed this time. Now, as long as we have y over x for this, there's a little bit of work. I get root 3 over 2 divided by what? Instead of dividing by 1/2, I'm going to take one step forward and say, look, I'm actually just multiplying by the reciprocal right off the bat. Something awesome happens. I just get root 3, right? Now, in this, I just want to highlight, and I can see it here on the work, that's really what I have, but I don't write it. Which means when I flip it, I can automatically see that from this flipped version, what do we get? 1 over root 3, and can I keep that answer? So how do I rationalize it? How do I fix it? Root 3 over root 3, that's my clever choice. I'm good with it. And then it turns into the square root of 3 over 3. And we now have our value of tangent. Okay, evaluating out these trig functions, we're going to get a lot of practice with it. So if it doesn't click like perfectly right now, that's okay. This is the very beginning of it. Sweet. Cool. We're going to go ahead and commit 10 minutes to the unit circle quiz. Okay, when you finish, I want you to check this out and at least the sine, cosine, tangent with this angle instead. And I know we haven't talked about it, so I'm just kind of getting a gauge for where you guys are. Drawing it would help, but we'll look at it here in a moment. So if you're at home, you should schedule a time for the unit circle quiz, preferably Tuesday in study hall. Sweet. When we make the change to this problem, did you guys draw a new triangle? There's not a right or a wrong, I'm just curious. What's different about your triangle, Rafa? So it'd be this triangle instead? Whoa. I assume it'd be this triangle instead? Now, if we think this out, if this is negative pi thirds instead, are these two triangles like the same shape, same size? So if all we had to do was flip it over the x-axis, what would this be? Whoa. Negative root 3 over 2? And then this distance would be, it'd be positive 1/2, right? Sean, you seem, there's something that, let me find a unit circle real quick. Where did you disagree? Why would we go backward? Why did you go backward, Rafa? Now, I'm going to change the language just a little bit. Why did you go clockwise instead of counterclockwise? It's a negative angle. Negative just says we spin clockwise. So looking at this, the only thing that I truly care about with this problem, not that it's not a fine and dandy problem, is I'm hoping that we can see a connection between these. The sine, the cosine, and the tangent. And we'll look at these together real quick. But because it's a negative angle, we just go downward. What do you see change about the sine? Instead of root 3 over 2, what happened? It's negative. What did you see happened with cosine? It's the same. And what about tangent? It's negative this time. Now, with these pieces, I didn't show any of the scratch work there, but it does work out like this. I would encourage you to double check it. We are going to use this to make sense of some pretty handy stuff that winds up happening. Do you guys ever remember like looking at functions like these? We'll come back to it. I don't want to spoil it. Cool. All right. Unit circle, just 48 points. There were 16 points. They were each worth 2. So there's your 32 points. And there were 16 points for which you had to give me the angle. 48 is your goal. Anybody feel like they got 48 out of 48? Anybody feel like they got 0 out of 48? You don't think you got a single problem right, Sean? You missed the day we talked about the unit circle, didn't you? That is not going to get graded at all for you. I completely spaced it. That's my bad. You weren't here. That makes sense. Okay. Let's continue on. As we're looking at these things, Sean, I'm going to give you my notes. I just got to take a quick glance here. That way you can see what we did last class, okay? Domain in period. You don't have to write this. It's just my guide. Even and odd. Cool. So, here are my notes from last class. On the left are my notes. So let's go ahead and knock it out. As we're looking at these things, they are functions, and that is easy to overlook and to forget. But because they're functions, naturally there's some stuff that we can talk about with these guys. So, as we go through, we're going to say our first little section is the domain and range. And we're only going to deal with the nicest of these functions today. So we'll say of sine and cosine. These are the two nicest functions that exist. Okay. Let's make sure we can see how we build these things up and we recall it, because this stuff is going to be so easy. When we think about domain, let's focus on that part first. We have spoke about domain extensively this year throughout separate chapters. What is domain? The x. Now, can you be more specific? The domain of a function is the set of x such that what? The function is true, or I would even argue defined. So if we're looking at a domain without any numbers, I'm just going to sketch a crazy function. Does this thing have a domain that's all real numbers? You say yes, and you say no. Do I hit every real number that exists on this graph for the x's? There's a whole interval right here where I never touch them, right? So my domain would be all the reals except for those. So it wouldn't quite be all real numbers. Now, when we think of traditional functions, we just plug in a number, right? F of 5, F of 7, doesn't matter. If I call it sine of whatever, instead of just being a number, remember we're plugging in an angle to represent it. Okay. Every input on a sine cosine is an angle. Whether it's in degrees or radians is irrelevant. Here's what I want you to think about for a second. If I give you a circle, and it could be the unit circle, that's fine and dandy, and you don't really need to sketch this unless you want to. I want you to find me a point on this circle where you can't find the x value or the y value. Is there any points on this circle that you can pick where there's not an ordered pair, x comma y? Could you find conceivably an xy at that point? Could you do it here? Or here, or here, or here? Is there anywhere that we can't? This is so easy. Because we can find an x at literally any angle you ever give me, and a y at any angle you ever give me, what do you think the domain is for sine and cosine? All reals. Every value works. No matter what amount of rotation we use, I'm going to find an x value for it or a y value for it. So that one's easy to knock out. The domain of, we'll say, sine. And here's a decision just to be consistent. I can call this sine x, which is pretty common to use x as an angle, but there's obvious issues if you use x with sine. I can use sine theta as my function, or I can use t for an angle. Do you care, x theta or t? Okay. So let's say the domain of the sine of theta is exactly equal to the domain of the cosine of theta. which there's an easy way to write this. All of them. Every real number that represents an angle you ever give me, I can find an x and a y for it. Quick check. What's the domain of sine and cosine? All reals. Easy. Okay. I want you to go a step further. This is important. We're going to use it. The range. I'm going to make the claim that these are also the same values, but I don't think they're all real numbers. The range of sine is the exact same thing as the range of cosine. What I want you to do with your neighbors, I'm going to pause this really briefly. I want you to identify for any x or any angle what's the largest and smallest x values that get spit out along your unit circle, and what's the largest and smallest y values that get spit out. I'll give you a second. If you need to check out a unit circle, there is a lovely unit circle on page 273. I cut this one out years ago, so I'll actually use this one. Is that at the beginning of the book? Weird. Like, where at the beginning? At the very, very beginning? That is bizarro. Thank you for that. I apparently did not cut it out. Okay, I'll throw a unit circle up here on the board. That's not the thing I need. Oh my gosh, I'm struggling. Cool. With your neighbors, about a minute, I want you to find me the largest and smallest x and y values that ever show up anywhere on the unit circle. 60 seconds, discuss it. Looking at this, people always get goofed up. Remember that we're not looking, when I'm talking about the range of something, we want to think x's and y's, that's natural, but don't confuse it with ordered pairs of x and y necessarily. I'm going to plug in not x or y into my function, I'm going to plug in theta. If I look at the cosines, what's the biggest x coordinate, regardless of the angle that causes it, what's the largest value of x anywhere in my circle? It's 1, and it happens right here. Everybody cool with that? What is the smallest x value of any point on this circle? -1. So conceivably, if I ask, and I don't know where it is, but if I said, does there exist a point along this unit circle where the x value is 0.0085? It must, right? Because I can draw a line from 1 to -1. Which means no matter what angle theta I choose to put in, I know it's always going to be between two numbers. What are those two numbers we just identified? -1 and bigger than 0. 1. How about the y values? What's the biggest y value that you're ever going to find anywhere on that circle? 1 is the largest. What's the smallest? And I can actually include those points, right? Because they actually touch it. So it turns out that if we look at this, eventually, the range for either of these functions goes all the way from -1 up to what number? 1. And we're done. It is a piece of cake to determine the range and domain of sines and cosines. Now, it's not our focus today, but if I go up just a skosh and I look at tangents, is there anywhere where this is an issue? Y divided by x. If x is 0, it's broken, right? And that's all fine and dandy. Is there an angle that gives me an x value of 0? It happens at 90 degrees, right? Or pi halves, and it happens at 3 pi halves. Apparently my tangents do not work there. We're not focusing on that today, but I just want to show you, like, hey, just think of the angle plugging in, and it's pretty straightforward. Straightforward is not the right word. It's reasonable when you think about it. Okay. Questions, thoughts, concerns, compliments? I am the coolest person you've ever met, JV. That's a great, astute observation. All right. We have another thing going on here. We can talk about the domain and range easy. Anybody, like, for real, no questions? That makes sense? Makes dollars. Good. Next thing, we are going to define a new word that sounds fancy, and it happens to have a lot of overlap with stuff right now. We're going to define for ourselves periodic functions. Okay. We're going to talk about the conceptual piece of this, and then we're going to really formalize it with the math. If I wanted to, let's say we're looking at sines and cosines. If I wanted to start at this x value, that's my cosine, whatever I'm at, whatever angle. How far do I have to go to get back to that exact same x value? Not just the same x like down here it would be, but how far do I have to go from, and I'll do it on the screen so people can see it. If I start right here, how far do I have to go until I get right back to that exact same spot? So I'm okay with 360, more okay if you say degrees, way more okay if you say degrees with it, but there's another value, 2 pi. Do you guys agree that if you're on a circle, no matter where you are, if you go 2 pi radians further, you end up at the same spot? Could you do that for n times, whatever number n is? Okay, when we define our periodic functions then, we're going to say that a function, or a periodic function, is simply a function for which, do you guys remember the symbol for there exists? Backward capital E. For which there exists a real number C that, and that should be such that, any function for which there exists a real number C such that the following is true, we get a periodic function. And we're going to look at this real quick. If I took f of theta plus some number, and it wound up being exactly the same thing as f of theta, this is a periodic function. There's some number that I can add to the argument of it that produces the exact same value. You guys just told me I have to go how much more along the circle to wind up at the exact same spot? 2 pi. So this is like if I take, and I'll use 360 for now because it's easier to think about. If I'm at 30 degrees and then I add 360, I wind up at the same spot and get the same value out of it. That's what's happening here. When we have this, the smallest number C, that, and I'm not going to write it, but that exists within this scenario, that smallest number, C, is the period of f. And I'm just going to say the period because we're talking about a function here. Now, if we just go one step further, we're dealing with the nice functions right now. For sine and cosine, what's that smallest number that I can add to wind up at the exact same spot? 2 pi. We're going to make that observation, and that's an important one. For sine theta and cosine theta, and there shouldn't be a comma there. For sine theta and cosine theta, the period equals 2 pi. Now, we're talking 2 pi radians. You would also be correct if you said the period was what, not in radians? 360 degrees. Now, notationally, when you see me write this, we're going to see that just notationally, if I write this down, I'll say the period of sine of theta is equal to 2 pi. You do not have to use this exact same notation unless you want to, but that's the notation that I'll commonly use. Anything crazy happening yet? I'm going kind of fast because I think you guys have seen a bit of this before, but I don't know how much. Ever talked about the periodicity of sine and cosine? Does it seem reasonable? Okay. Now, there's another like a graphical interpretation of this that we'll see once we start graphing these. One more little piece, and it's the last one. In white, don't write, but if I look at this function here, and I said, does it have symmetry? Does it? Now, this is way back early in the year, but I'm going to make a claim. This function, I know that if I went to this number a, whatever it is, it spits out this y value, f of a. Everybody good with that? If I go over here to negative a, what y value does it spit out? So it's f of negative a. I agree, but do we really have to write it any differently? Like if we just did it here and said that's 5, what would this one be? 5. Do you remember what we call functions that do this? One more time. Not necessarily absolute. If you go back, and I don't know that I really want to make you look at chapter 1, but I asked you early on the first test, is this function even or odd or neither, and to justify it. If we have a function that when I do this, it's exactly equal to this, we have a symmetry. And that's what I see happening right here. Do me a favor, check with your classmates or with your notes. I want to know, is this function that I'm seeing right here even or odd? Chapter 1, I think, like probably the third or fourth day of class is when we discuss this. I'll give you a moment, and as you're doing that, I'm going to steal my unit circle back up here on the board. Did you already find it? What section was it in? 1.5. So in 1.5, now I don't expect you guys to draw the unit circle every time I reference it, just so you know, but I'll keep throwing it up on the board here for you. Okay. In 1.5, we had a definition for what it meant to be an even function and what it meant to be an odd function. As I look at the unit circle, and I'm going to reference this a bit here, but let's go ahead and add one more little tiny section about even and oddness of these functions. Trig functions, and even or odd. Okay. When we look at this, we're going to see that the same thing happens that we saw in chapter 1. It just looks a little bit different because we have to think about it on a circle. First off, if we look all the way back, and this is just a recall, if I ask you to determine if a function is even or odd, there's always a first step. You begin by evaluating f of negative x. If it spits out, and this is going to be two different options, if it spits out the exact same thing, f of negative x is the same thing as f of x. Was that an even function or an odd function? It's even, thanks to Abigail's notes. We just say it's even. This is even. In contrast with that, maybe, just maybe, it spits out the exact opposite, and you get negative f of x. In this situation, this is what we call an odd function. Okay. This is just a mathematical way to say, is there symmetry, and is it about the y-axis, even, or is it about the origin, and we would call it odd. So I'm going to use this circle up on the board. You do not have to sketch it out, but we're just going to check out some stuff. Give me a positive angle you want me to plug in. Charles, any positive angle in radian or degree, don't care. 45 degrees, so check it out. Here's a positive 45 degrees. So if I said, okay, what's the sine of 45 degrees? Could you guys tell me? Root 2 over 2. Now, I'm going to try to do the exact opposite. I'm going to make that argument negative this time. The sine of negative 45 degrees. I can't see my cursor when it's up there. Here's negative 45 degrees. What is it? It's negative root 2 over 2 this time, right? Did that show me that if I replaced it with a negative, did it give me the same value or did it the exact opposite? Check it out. The fact that we know that sine of theta, and I'm going to change that, sine of negative theta, oh my goodness, there we go, is equal to sine, negative sine theta. This implies that sine is a what function? Sine is odd. Now, there's more to it. If sine is odd, what do we call it when we just flip sine upside down? Instead of y over x, we have, or sorry, y over r, we have r over y. Back to our definitions. If sine is odd, what else do you think is going to be odd? Cosecant would also have to be odd. So we have sine is odd, and I'm having a heck of a time finding this, but so is cosecant. Sine and cosecant are both odd. Because if it's just a reciprocal, I know that the same sign change is going to happen. Okay, if we contrast this, I'm going to leave a little blank space here. I want us to think about the same thing with cosine. Riley, give me any cosine or any angle that you want to talk about the cosine of. So 30 degrees. What's the cosine of 30 degrees? Okay, cos 30 is root 3 over 2. And I'm just going to check the opposite. So cosine of negative 30 will go down to here. Barsega, what's the x value at negative 30 degrees? Square root of 3 over 2. Is it the same? So what we just demonstrated just now, just by looking at it one time, is that if you were to give me the cosine of an angle theta or negative theta, it is exactly equal to the cosine of theta, which means that this is what? Even. Now I'm going to write this one a little bit differently and wish I'd done it differently here. I don't have my notes in front of me, is why this is coming out a little bit clunkier. But check it out. Cosine, and what's just the reciprocal of cosine if we just flip it? Secant. Cosine and secant are even. All right, we're going to get one more and we're going to determine if it's even or odd real quick. Because we've talked about sine and cosecant. They're odd. We talked about cosine and secant. They're both even. Based on the formatting that I've gone with, you can probably make an assumption, but I want to verify it's true. I'm going to pick a tangent that's really easy for us to think about. I know that tangent is defined as what? How do we define it the other day? Are you y over x, sine over cosine. Sorry, we haven't talked about that. Y over x. Check it out. If you check, I'm going to use 45 degrees again because it's really convenient. What's the tangent of 45 degrees? It's 1. Root 2 over 2 divided by root 2 over 2 is 1. What if we did negative 45? So what you just, and I agree with you, you just found in general that if we take the tangent of negative or of theta, the opposite of that is exactly what the tangent of negative theta. And I don't know why I switched order, but that's the same thing that we've been saying, just switched around. Is tangent even or odd? And I'm going to switch this because that's the way we've been doing it. There's a scratch work. I'll get rid of that one. It's odd. If tangent's odd, what else do we get for odd for free? Cotangent. So, one more. Tangent of negative theta, I'm writing the same thing, is equal to the negative tangent of theta, which implies, I'll do it here, tangent and cotangent odd. Now, we are just like, I'm blasting a ton of information at you really quick. All of this stuff will wind up being used, but it's okay if that doesn't click exactly perfect right now. We get so much practice with all this in the next 3 chapters. Like, don't stress. It will get built up as we go. Okay, as a big look at everything, here are all the notes, and we can't really see them. Just purely, I know you don't have a good gauge. Thumbs up says, man, Trig's going pretty well. It's easier than I thought it was going to be. Thumbs down says, oh my gosh, I hate it. Please stop. Anywhere in between. Where would you say you're at? Okay, so nobody's like crying as they're pointing down to the other side of the planet, which is good. we're going to get a little practice to see whether your assumptions are like correct. So you get some homework tonight. And your homework, you get 5 minutes right meow to look at it. Your homework tonight is homework 4.2, and I know it looks like a lot. Don't write 1 through 4. We're going to chat about them at the start of class. I will just omit them now. 1 through 4 we'll talk about at the start of class tomorrow. Make sure our academic language is there. The real homework that I want you to do is numbers 4.2, page 277. Number 5, 19, 21, 24, 31, 32, 37, 39, and 60. Cool. We get 5 minutes to start. I want you to start. Let's do it to it. It's awesome. Yeah, that's fine.